Welcome to another UWS-1 design video from the Ultralight Airplane Workshop. In this video, we're going to work on the chord distribution load of the vertical tail on the UWS-1 Ultralight airplane. This is part 2 of a two-part video figuring out the distributions of load on the vertical tail of the UWS-1 Ultralight airplane. Now, first one, we talked about the span distribution load. If you haven't seen that video yet, I'll put a link to it up here in the upper right-hand corner. But in this video, we're going to work on the chord distribution load. Let me use a prop here. Now, this is just a rudder plug, but make believe it's the whole vertical tail. So in that part 1, we worked on how the load is distributed along the span. In this video, we're going to work on how the load is distributed along the chord of the vertical tail. Well, let's get to it. We are going to be determining this chord load in the same flight condition as we did for the span load. In other words, at the maneuvering speed, v sub a, with the angle of attack on the vertical tail being 16 degrees and the rudder being deflected 25 degrees. And again, here's our airfoil with the rudder deflected 25 degrees. And don't forget that the calculation that we're going to do here for the chord load won't be quite right. It'll be good enough for this first cut at determining the chord load, but we actually have an elliptical nose on our rudder, and the software we are going to be using basically sticks in a plane flap without a gap. We're going to have a gap, so our actual behavior will be a little bit different, but for this first cut at our design, it's good enough. And just kind of give you a little feeling for where we're heading, this is the chord load distribution. Let's do a quick review of what I'm trying to accomplish. A lot of this I covered in part 1 of the video. And in part 1, we're trying to figure out the span load distribution on the vertical tail. What we're looking at here is half of the tail of the UWS-1 Ultralight airplane. So here's actually the center line of the horizontal tail. Here is the right-hand side or starboard half of that horizontal tail. And here's the starboard vertical tail. Here's the vertical stabilizer, and here's where the rudder is. And so, like I said, in part 1, we are figuring out the load distribution of the vertical tail. Now, load distribution should be roughly the same for the stabilizer as it is for the rudder. Roughly. Except out here at the tip, they'll be a little bit different. But since the tip has so little lift, we're not going to worry about that difference. But that's only part of the story. We also need to know the chord-wise load distribution. The reason we need the load distribution along the span is that we can figure out how to handle the bending loads when the load is applied sideways onto this vertical tail. We're going to have a spar running down here at the vertical stabilizer, and we need to know how to build that spar to handle that load. And same sort of thing with the rudder. We'll probably have a spar in that, and we need to know that load along the span in order to build the spar to carry the load to the hinge points. We need to know the chord load distribution also. This will help us figure out the shear load on the skins of our vertical tail, the horizontal stabilizer, and the rudder because of twist that occurs. Typically, when you have a chord load, you're going to have more load at the leading edge and less load at the trailing edge. Now, let's say that load is into the screen, going in like this. That will cause this leading edge to start pushing in the same direction as that load. And as you go along the span, that twist is going to get greater and greater. Now, I'm assuming that there's no twist here at the bottom. And that twist is going to cause a shear load in the skins of a vertical stabilizer. And the rudder is something similar. It's got a little more load at the leading edge or the hinge than it does at the trailing edge. So it can twist also. Now that twist will kind of depend on where your control is. If the control is down here at the bottom, then the twist will progress as you go up toward the tip. But if that control is here in the middle, then the twist would progress the same direction as you went down toward the root and out toward the tip. That shear force or shear load will be greatest wherever your flying surface is held rigidly, and it'll be least wherever your flying surface has the most freedom of movement. The shear load is 0 out here toward the tip, and as you get closer and closer to the root, the shear load increases. We did our calculations for the load, assuming a speed of V sub A, that's our maneuvering speed. In our case, it turns out to be 73.1 knots, and with our rudder fully deflected to give us a maximum coefficient of lift. The reason we went for a maximum coefficient of lift at V sub A is that we want this rudder to stall before it structurally fails. Well, let's proceed on and find out how we can calculate that chord load distribution. I want to give you a quick look at what I used to use for vertical tail load calculations. This is a figure from the old Federal Aviation Regulations Part 23 Appendix B. This is supposed to help you figure out how to do that span load on the vertical tail. I've decided I'm not going to bother doing this calculation for the UWS-1 Ultralight airplane. And the reason for that is this is no longer in Appendix B of Part 23. I mentioned that in the Part 1 of our video. Finally stumbled across something that let me know what happened to the old Appendix B of Part 23. I finally ran across this Federal Aviation Administration Advisory Circular 23-19A, and it covers the guide for certification of airplanes that are trying to comply with Part 23. I was going down through this and I came down to the control surface loads area, and I found out that this control surface load information that used to be in Appendix B of Part 23 was removed for Amendment 2342. They amend these various parts of the regulations once in a while, and this particular amendment removed Appendix B. That's because these calculations seem to be a problem in certain situations. You were getting inappropriate surface loadings for high-performance airplanes, airplanes that had the wing spar located after the 25% part of the chord of the wing, and aircraft that have the horizontal stabilizer leading edge not attached to the fuselage. And there's something similar to this for lots of the other parts of Appendix B, and I guess that's why they removed it. I'm going to quit using Appendix B for my calculations. I have been using the information I was getting from VSP Aero and some other applications to do the design. So this isn't a great loss, but it's kind of disappointing that you don't have this anymore. Well, since we don't have Appendix B, let's go ahead and figure out how we're going to calculate our span load for the UWS-1 Ultralight airplane vertical tail. As we did in Part 1 for the span load distribution, for the chord load distribution, we're going to again use VSP Aero to get an initial assessment or estimation of what this chord load distribution is going to be. So in order to run VSP Aero, we come up underneath the analysis menu, we pick VSP Aero. I still have a lot of the information set in here that we had before. We're going to use the Vortex Lattice method. In particular, and I learned this just recently, with version 3.21.1 of OpenVSP, if you use the panel method and you want to deflect, in our case, the rudder, but I think that's true for any control surface, the panel method does not handle deflection. So you can come up here under your control group angles and set an angle and it'll end up being ignored. Now I know this had been working in the past, so they must have run into a problem and they've disabled it. So we are going to use the Vortex Lattice method. I'm going to get all of my reference data from the model. I have a control group that has the rudder in it. And I'm going to do another thing, which is kind of neat. I got to get this chord load information in at least one place, and I should probably get it in several places. Now, according to the FAA, you really only need to do one estimation, and then it works all the way across here. Now, I happen to know from looking at some pressure values that I did using the panel method that my span distribution is not the same down in this area as it is here in this mid area. Now I know the tip's different. I'm going to ignore differences in the span load on the tip. But I happen to know down right here I get a little bit of different behavior. And part of that, I believe, is because of this angle here. When the vertical tail is at a significant angle of attack, I think a vortex is probably being created because of this angle. And it's giving me a different pressure distribution in this area than it does here in the mid-span area. But that's a small enough span that it's doing that. I think I'm going to ignore that and just use what I get here from this mid-span area. But how do I get that? And how in the world did this show up? You come up here under the Advanced tab. you come under CP slicer. So this is the pressure coefficient slicer. You hit the add slice and it puts one in here, and then you say where you want along the span for that to occur. Now I want it to be in the Y direction because if you remember right, we've tilted this thing over 90 degrees. So if this is actually now horizontal in the simulation and this is vertical. And as I mentioned before, that's because OpenVSP likes to do its calculations in the plus Z minus Z axis. So I need to flip it over 90 degrees so that this would be horizontal. So I had to say Y here. I can either show the cut or not show the cut. And I'm 24 inches. This is about the mid-span area. If you remember before, this is at about 4.5 inches, and this is around 48 inches out here. So 24 inches is about the mid-span. Well, let's go back to our overview. I'm using an angle of attack of 16, which is the same angle that I used when we were doing the span distribution. And my rudder is deflected down 25 degrees. And 25 degrees is the maximum deflection we're using. Let's just go ahead and do a run. We'll launch the solver. Now this is the load distribution, and that looks pretty similar to what we were getting before, so that's good. Now let's come up here to this CP slice tab. And what this is showing is a difference in the coefficient of pressure. What it's doing is showing you the difference in pressure between the bottom of your airfoil and your top of your airfoil. So it's not showing you both top and bottom, which we'll get to see here shortly. This is showing you the difference. So this is basically showing you the pressure pushing up or pushing down. So these positive numbers means that it's pushing up, it's lifting. Now if it went negative, which it doesn't in this particular example, it would be pushing down. So you could use these numbers to get your chord distribution. And you'll notice that this area right here is roughly where the hinge is on the rudder. That's why we have the sudden drop off here. Now this distribution doesn't quite match what the FAA was showing us in their little diagram. This area is very flat here, and there's a very small increase along here. Not as much as I think they're showing. This front part might be about right if you summed them up. I mean, it comes up really quick here, but if you took this front 15% and averaged them, it's going to be probably in this area. Now this is nice, but it doesn't give me the information I want. In particular, I would like to know what the drag is on this rudder also, because when I'm going to do the structural design, I need to know how much force either back or forward this is incurring. So I really need the overall bottom and top coefficient of pressure. This is kind of nice for just doing the chord load across here, but it's not sufficient for what I want. So the next question is then, how are we going to get those coefficient of pressures on the top and the bottom? We are going to use something that we used way back in the past when we were working on airfoils. We're going to use XFLR5. All right, here we are in the XFLR5. The version we're using right now is 6.47, and it kind of looks like that's going to be the last version. The developer for XFLR5 is moving to another application called XFlow, I believe it is. And it's going to be something very similar to OpenVSP as far as I can tell. But he is going to charge some money for that once he gets through his beta testing. So once he gets that up and running, we may give it a little test and see if we like it. But for now, we are currently in the direct foil design section of XFLR5. And I've loaded in the airfoil that I intend to use on the tail of the UWS-1 Ultralight airplane. And the airfoil for this is called UWS-1 Tail 12. And I'll put the 12 in here because the thickness is 12% of the chord. The rudder on our vertical tail takes up 45% of the chord, and maximum deflection is 25 degrees. So I used XFLR5 to make a new airfoil that looks like that, and that's this blue one here. And so it made this, and so we're going to do a couple calculations on the undeflected airfoil and then the deflected airfoil. Let's jump over and take a look at that. In order to do that, we're coming up underneath File, we're coming down to Airfoil Direct Analysis and clicking that. And we want to look at coefficient lift, which is graph 2. So here's our coefficient lift. This blue one is our 25-degree deflected rudder, and here's the non-deflected rudder. Now it looks like our maximum coefficient lift is 1.7. Now I used 1.65 before. I'm going to go ahead and stick with that. We're going to do our calculations on this airfoil. We are interested in its behavior here at the maximum coefficient of lift. So that is an angle of 11 degrees. Next, we're going to come over and we're going to look at the operation points. Let's click on that. So we got 11 degrees selected. We're going to come down to our 25-degree tail. By the way, our Reynolds number is about 1.3 million here, in case you're interested in that. We want a couple of things. We really aren't that interested in looking at the top and bottom coefficients of pressure. It's kind of useful, but there's actually something better, and that's this here. This shows the magnitude and direction of that pressure. And to do that, you click on pressure. Now this red line is your boundary layer, and that's called displacement thickness, so you can actually see where the boundary layer separates. If you look at technically, it's separating close to the nose, but it stays fairly closely attached, and it's going to be turbulent until about here, and then it really starts separating out. The bottom layer stays attached farther back. Let's take a look at those numbers. You can look down here at upper transition. So it's actually transitioning right out here at the nose, it claims. It's going from laminar to turbulent out here, but it still stays fairly closely attached. On the lower surface, we got lower transition. It actually makes it back to half of the chord before it trips from laminar to turbulent and starts separating. So that's actually pretty good. But let's come back up to this big old purple dude here. So these purple lines are showing you the coefficients of pressure. And the direction is normal to the surface, or you can say perpendicular to the tangent at a surface. So this is showing you how the pressure is acting, the direction it's acting. You can see there's a lot of suction up here at the nose. A tremendous amount of the pressure is being pulled. These arrowheads show the direction. So in this case, it's suction. It's pulling away from the surface. Here on the bottom, you can see the arrowheads are pointing into it, so it's pressure pushing into the surface. So you can see this nose up in here is really trying to be sucked away. So that's why I wanted to have this information, so I can figure out which direction I have when we are talking about perpendicular to the chord line, because I needed to handle my vertical tail structure to handle that load. Now I also need to do a calculation on this at my maximum dive speed, because then a lot of that's going to be pulling it backward. So we need to be able to handle that. Well, this is all fine and good, but I actually need some numbers. We need to get to these numbers on these pressures. I did a right click to bring up this menu. We come up to the center pressure graph. We come down to export graph. Click that and then specify what file name we want to save our data to. I'm then going to import that data into a spreadsheet. Another thing that I want to do is save out the coordinates for this airfoil with the rudder deflected. The one I have is for the airfoil with the rudder not deflected. So I come back under File, come back to the Direct Foil Design, right click underneath this 25-degree airfoil, select Export. And just so you can see what that looks like, what I've done is I've imported that file here into LibreOffice, a calc application. And by the way, let me show you that in the text file. So here's what it looks like in a text file. These are just line numbers over here. It's not actually part of the file. So you're going to have a coordinate here on the left side where 1.0 is the trailing edge, 0.0 is the leading edge, and these are the y coordinates or the thickness from the chord. So negative is below the chord. Now when you load this into your spreadsheet, if you're going to do that, you want to use space separator if your spreadsheet allows you to do that. And then when you get it in, this is what it's going to look like. That CP graph that we exported before from XFLR5, I've loaded it into a spreadsheet so you can see what it looks like. So this header is X. So this is the chord position. And again, you can see it started at the trailing edge. Very similar to what we looked at for the airfoil coordinate. And these are the pressure numbers. So this is the coefficient of pressure. So pressure along the top, moving toward the nose, wraps around the nose, then comes back toward the tail on the bottom. That's all well and good, but we need more information. Before we really get into the details on that spreadsheet, let me talk about what the spreadsheet is going to be doing for us. Imagine that this is the airfoil on our vertical tail. It's not. This one actually has camber to it. The one on our vertical tail is actually symmetrical. But ignore that this isn't symmetrical. We have a chord line on our airfoil. 0.0 is the nose. 1.0 is the trailing edge, like we've talked about before. And we're going to have our rudder deflected 25 degrees. What I want to find out is the pressure distribution normal to this chord line. In other words, perpendicular to the chord line. But all of our pressures are given normal to the surface, so perpendicular to the surface. So for example, back here, it's going to be in this direction. Up here, it's going to be in this direction. So what I need to do is find the chord normal component of the pressure, and then also find the chord collinear portion of the pressure. That would be our drag component. Vertical is going to be our load component. But back here on the rudder, it's different. We want to know normal to the rudder chord line. So the rudder is going to be done just a little bit separate. It's going to have different angles. And of course, if I had drawn out the surfaces of the rudder, it'd be something like this. And so the pressure as it comes out of the computation is normal to that surface. So it's going to be back this way a little bit. Whereas normal to the chord is just a little bit more than an angle, up this direction a little bit. What I've drawn down here is kind of an exaggerated version of that. So if you can think about points that are up here, and these airfoil coordinates are individual points. And so that's what these little circles are representing, the positions of the individual points on the airfoil, and that would be something like up in here. And those pressure values we have are at those coordinate points. Like, for example, this gray line I have here, this would be the pressure value at this coordinate, although we don't have an angle for it. We just have a magnitude. What I need to do is figure out the angle at this spot. So the way I did that this time, and there's a number of ways that it could be done, and they'd all be perfectly valid, but since our points are so close together, I decided to do a simple average of slopes. So what I do is calculate the slope between the desired point and an adjacent point in one direction, so this would be slope 1, and on the other side too, I figure out the slope between our desired point and the next point in the other direction, so this would be slope 2. I then average those two slopes to get this slope here. So this will be the slope between these 2 points averaged. It's not actually the slope between those 2 points, it's the average value. I probably should not have drawn this line connecting these 2 points. Then I'm going to assume that the direction of this pressure value is normal or perpendicular to this slope line I've calculated. So that now gives me an angle for that pressure line. What I want though is I want the drag direction collinear to our chord, and I want to know the load direction, which is perpendicular to our chord. And what I can do is use sine and cosine. So this value would be the sine, this value would be the cosine, assuming that chord is a 0 angle. So the sine of this angle multiplied by the magnitude, in other words the pressure, will give me the load pressure perpendicular to the chord. Or if we're on the rudder, all this will be tilted, and it'll give me the pressure perpendicular to the rudder chord. So when we look at the columns in this spreadsheet, what I'm doing is calculating intermediate values and then the final value. So let's take a look at that real quick. Okay, here's the spreadsheet. I started with that export of the CP graph from XFLR5, and so here are those 2 columns. So this is the x-coordinate along the airfoil, and this is coefficient of pressure at that spot. Now it starts at the top, at the trailing edge, and it proceeds on like we've talked about before. Now to help myself out a little bit, I drew some lines in here, roughly where the hinge line is for the rudder. And then I also imported the airfoil coordinates. So here again is X coordinate for the airfoil, and I made sure that these matched up. I just wanted to make sure that the airfoil that I got from the CP graph was the airfoil that I intended to use. So that's just a matchup. And again, here's the thickness. So these two together are the coordinates for our airfoil. So just as a sanity check, I made a graph of that airfoil coordinate system. And so this should look very similar to XFLR5. Come back here. So it looks about right. Let me get that back out of the way for a moment. I'm just going to quickly talk about what I calculated along here. So I calculated slope 1 and slope 2, so that each of these x's, except for the very last one, and the nose at the 0 coordinate, I calculated a slope on one side of that point and then a slope on the other. Then I took the average of that slope. So slope 1, slope 2, average. I then figured out what the angle of that surface was using that slope. So for example here, at that trailing edge, that slope angle, let me bring that back up here. So this line here, right here at the tip, is 33 degrees. So from horizontal down, that's negative 33 degrees. Now the chord, which is going to be a line through here, which isn't drawn here, is minus 25, so that's a deflection angle of our rudder. And then what is the normal to this minus 33? You're basically just adding 9 degrees. So the normal to this surface right down here is 56 degrees. Now that I know the angle of the chord, and I know the angle that's normal to the surface, I can calculate the portion of the coefficient of pressure that is the load component. In other words, the component that's normal to the chord. And the portion that's 90 degrees to that, which would be collinear to the chord or parallel to the chord. So just a quick review. The portion that's load, that's normal to our chord, and the portion that's collinear to the chord. That'd be the drag portion. Since I've calculated all these coefficient of pressures that are normal to the chord, I can calculate the difference on those coefficient of pressures. Now, if you remember what we had VSP arrow calculate on that CP slice, it gave us this DCP, the difference in coefficient of pressure. So that's what I have in this column. I went to the same location along the chord on the top and on the bottom side, which is down lower, and I took the difference on those, and that's this value here. So a negative value means it's pushing down, and a positive value means it's pushing up, normal to the chord. I did the same thing for drag, except I just added those up. So a negative is pushing, in this case, toward the nose. A positive would be pushing toward the trailing edge. And one thing I wanted to point out, in this column, I'm assuming that the chord is only the vertical stabilizer chord. So I kind of ignored the deflected angle of the rudder and did the calculations without that deflection angle all the way across. But I did want to know what that was for the rudder, so I made another column over here. So this is difference in coefficient of pressure for just the rudder. In that case, it does take into account the rudder deflection. And I happen to have some pretty little pictures to look at to demonstrate that for you. So here are those differences in pressures. Now this orange one is the vertical stabilizer. So this is difference in pressure all along it. So this is the nose over here to the rudder hinge. And then I have two lines here that are both rudder. Now this blue one is not considering the rudder to be deflected. In other words, I said the chord was still 0 degrees angle here. And you can see that it's just a little bit lower. This yellow one, which is really hard to see, is just a little bit higher. And the only difference there is just because of the angle we considered the rudder to be. So it almost wasn't worth doing. But when we consider the forces normal to the rudder chord when it's deflected, it is a little bit higher force. So when we're designing the structure of the rudder, we're going to use this higher one. All right, now the next thing to calculate is what will be our load per square inch. When we go to start doing static load testing on our tail, we're going to want to be able to put sandbags on it. So I need to know how much load per square inch. And then I can calculate, well, what's the area that the sandbag would take up? And then how many sandbags do I need to load on there to get the right load? So that's the next thing we'll look at. So as an example, I went and looked at an area on the vertical stabilizer where the chord was 20 inches deep. Then I recalculated what the inch values would be for the airfoil coordinates. So I converted from those 0 to 1 airfoil x coordinates to what the chord would be at those same locations with a chord of 20. So you can see the very last point, or trailing edge point, is at 19.15 inches. And of course the leading edge would be at 0 inches. But to make it a little bit easier on myself when I'm trying to deal with adding sandbags and such, I then divided up that chord into inch increments. So I started at 19 inches at the trailing edge and then went in 1 inch increments up until we got to the leading edge, except for this little 0.2. Now there's going to be some little spreadsheet magic here because I want to convert from these difference in CP values, which are at those X coordinates. I'm going to convert that into these inch coordinates. So I have to do something called interpolation. And this is a little bit harder to read because the value here, what I'm doing is I'm taking the difference value here and difference value here and averaging them, multiply it by 1 inch, and then put it in here. So you'll see that this value here is usually halfway in between these. So this 0.45 is in between this 0.262 and this 0.284. So you can think of this as a pressure per inch. If you multiply by another inch, so this would be the pressure per square inch at about 18.5 inches back from the leading edge at whatever that span location is where we have a 20-inch chord. I know it's a little complicated. I'm trying to get through this quick. Now, this is going to be the load along our chord. So I'm going to sum all these up to figure out what that total load is. That's 32.6. I then went and looked at the results that we got from part 1 of this video, and I found out where 20 inches of chord were. So I found out what the load was there for an inch wide strip along that chord. So the total was 2.784 pounds. Now that I have this information, I can find out how much load in pounds there is in each square inch from the tail to the nose. So that very last square inch at that trailing edge is 0.0048 pounds of pressure. Up here at the nose, the very first square inch at the nose is nearly half a pound. It's 0.437 pounds. And just as a sanity check, I want to load up all these square inches of pounds, and this value should match this value, and it does, so I haven't made a calculation error there. Now let's go down and look at the graph of this. So this is a graph showing me the load for every square inch going from the nose to the trailing edge. And the shape of this pretty much matches the shape of this one. It's just averaged out a little bit more. Now that's only for one spot along the span. Now it'd be a heck of a lot of work to go along every inch position along that span and do this calculation. And it's really not necessary. What I'll do is I'll take one at the root, I'll take one out within about an inch or maybe 2 inches of the tip, and then maybe 1 or 2 more in between. So I have about 5 locations from the root to the tip, and I'll interpolate these values in between. And that'll be much easier to calculate. Well, we managed to get at least one chord load calculation done for this vertical tail. And as I just said, we'll do a few more spots along the span to get some chord load distribution numbers. Another thing I need to do is I need to do the same thing again, except do it at the dive speed. And the main reason for that is that I want to know what the maximum drag I should expect on that vertical stabilizer, because I need to design the structure to be able to handle that. And while I'm at it, I'll look at what that span-wise and chord-wise distribution is to see if there's something unusual going on there that I need to take into account. I want to thank my fantastic sponsors on Patreon at the designer tier level, Richard and Keith. You guys are fantastic. Thanks for supporting the channel. If you haven't subscribed to the channel, think about doing that. And if you like this video, hit the like button. Also, don't forget that we have a Facebook page, and there's a link to that down in the description. I'll put a lot of little clips and photos on that I won't normally make it into a video. Well, that's it for this video. Until next time. Welcome to another UWS-1 design video from the Ultralight. In this video, and the reason for that, and the main reason, and as I said before, I'll do some more span-wise. And as I said before, I'll do some more what do you want? Hi there. How you doing? You want back down? What do you want?